Made the wise move a few years ago from, was it Braunschweig?
Bochum.
To Bochum, to Dundee in Scotland, where he's been now for several years.
Yeah.
And so here he's going to tell us more about magnetic braids.
Yes, thank you. So when Keith suggested that I give another talk here, I first was hesitating because I thought there would be a little bit of overlap with the previous talk and possibly also with the talk I'll give in October in the other workshop. But then this is a good chance to go into detail, a bit more details in one or two of the aspects. So what you're going to see is some part which you might have seen already a few weeks ago, and some new stuff which you can find in further detail in preprint, which is now on the archive. So just search for these names of Anthony Yates, with whom I did most of this work, and myself, and you will find some paper on this. Okay, so the title of the talk is Magnetic Braids, Hamiltonian Action and Selective Decay. Most of what I will say can be applied also to vortex fields or vorticity fields, or if you want, even to velocity fields if they are divergence-free. So the magnetic fields are kind of motivation, but the mathematical concepts apply to other fields as well, as long as they are divergence-free. So what you see here is the motivation, and Konrad Bayer told us a little bit about this in his talk already. This is the surface of the sun, and these faint structures are coronal loops, that is magnetic field lines on the surface of the sun. To be precise, what you see is actually the plasma, which is tightly following these field lines, and the plasma is very, very hot, and an unsolved question in solar physics is, why is this plasma so hot, and in particular much, much hotter than the surface of the sun? The surface of the sun has about a temperature of 6,000 Kelvin. The coronal loops have temperatures of 1 to 2 million Kelvin. So this is our motivation. We look at one of these loops and we ask the question, how does this loop become so hot? The only source of energy available which could provide sufficient energy to heat these loops is the magnetic field itself. So in the 70s, Eugene Parker, quite eminent solar physicist, came up with the idea that the motion of the on the boundary of these loops, so at the foot points of these loops, which are anchored in the solar surface, the motion of the plasma on these foot points braids these fields, and that stores energy in these loops, and then this energy can be released. And if you want to make a simple cartoon of this, then you can straighten out this solar loop into a simple cylinder. So the foot points on both sides of the loop correspond to the lower and upper boundary of the cylinder. So you add some motion here on these foot points, so you braid the field, you increase thereby the magnetic energy of the system, and then you ask, what happens if I let this system now relax? And depending on the difference between the energy state of this system and that system, you can gain some energy which in principle could heat the plasma. Now, in order to determine this difference in energy between the braided state and the relaxed state, we have to know a little bit about what a relaxed state could look like. So if we think of our plasma as a magnetic field, then it has a magnetic energy together with a flow field, which has a kinetic energy, and possibly an internal energy. Then in these astrophysical plasmas, or in particular these plasmas on the Sun, the internal energy, even though the temperature is so high, is usually quite low compared to the magnetic energy and can be neglected. This is because the density of these plasmas is very, very low. So if we then we can minimize the energy of the overall system by setting the velocity to 0, that sets the kinetic energy to 0, and then we look for the stationary states or stationary points of the magnetic energy. So that yields then the so-called Beltrami or force field free fields. So they minimize the magnetic energy. Not necessarily, these are extrema of the magnetic energy. And in general, there appears a parameter lambda here in this equation, which is a force-free field parameter, and in general depends on x, the position. There is surprisingly little known about the existence, uniqueness, well-posedness of boundary problems, and so on, about these fields. Most of what is known about Beltrami fields is for some kind of symmetry, so essentially 2D cases. The problem is quite tricky. The equation looks simple because it looks as if it's linear, but if you take the divergence, you see that because B itself is divergence free, that this function lambda has to be constant along field lines of B. So lambda is not something which you can simply impose, and that makes it a complicated nonlinear problem. So the question is, we have a comparatively large class of ground states here, or states which can possibly minimize the magnetic energy, and which one do we choose for our problem? So what determines this lambda? Now, the hope is that we can find some kind of property of our initial state which somehow relates to this lambda. Or with other words, there are some kind of invariants which survive this relaxation process and which determine this lambda. Now, formally, we could make a distinction in this relaxation. We could divide the whole process into two subset processes, which is first an ideal relaxation and then a non-ideal relaxation or resistive relaxation. And then we could look at possible invariants of these two stages of relaxation. Now, for the ideal relaxation, almost all is known. We have an ideal induction equation, which, if you are a mathematician, you would probably write it with the Lie derivative. And then one can see that the magnetic field time 0 is just the pullback of the magnetic field at the time t under an isotropy g, which is given by the flow of this velocity field. And this then implies the conservation of flux, which is essentially Fein's theorem, for any co-moving surface, co-moving, that is, moving with the flow G. And also the conservation of helicity. Here, A is the vector potential of B, and in principle you should also integrate over a co-moving volume here, but usually our volume is the whole domain, that is our cylinder. And this is by definition co-moving.
How do you conceive of the energy decreasing during this phase?
Say again, how do you?
Well, ideal relaxation, the energy is decreasing.
Yes.
What's the mechanism?
It shifts energy from the magnetic field into the kinetic field usually.
And then how is it dissipated?
Then via viscous.
So it's a viscous.
That would be a viscous.
medium.
Yeah.
Ideal only in the sense that the conductivity is infinite,
Yes.
but not ideal as far as viscosity.
Correct. Yes.
Yeah.
It's slightly artificial.
Yes.
But
I
yeah.
thoroughly approve of this. Just want to be clear.
yeah. No, that is correct. Okay. We have further invariants here, of course. In principle, the field lines, or the field line mapping from the lower to the upper boundary is an invariant. Okay. So, in principle, we have, if you want, infinitely many invariants here. Now, for the resistive relaxation, we are in a much more difficult situation. Strictly speaking, if you wait long enough, then the system will relax to the state with the lowest energy consistent with the boundary conditions. So the boundary conditions would be prescribing the magnetic field on the lower and upper boundary. So that would be a potential field in the volume, and this has kind of no topological information left from the initial state. So you could say there is actually nothing which survives a resistive relaxation. Everything ends up in the same state, whatever you start with, as long as you keep the boundary conditions the same. So this looks slightly desperate then. There seems to be no further information. However, this is not quite what we are looking for. And the reason is that this equation, this resistive equation, if you write it in dimensionless quantity, you have here something like 1 over Rm Laplacian B. That this Rm, the magnetic Reynolds number for plasmas in the solar corona, is pretty high. So you have something, depending on who you ask and which situation exactly, you can have things between 10 to the 8 to 10 to the 12. Okay. Maybe I shouldn't write this that way. So this is a very, very small term in general. So this means also that the time you have to wait for getting to the state of the potential field would be very, very, very long, even if you want to just allow some kind of approximation of this. You would have to wait a very long time, much longer than what is observed, much longer than the time scale which is observed on the Sun, on which these structures relax.
How much time do I have to wait for the viscous term to take effect?
Even longer.
Even longer?
Yes. So our process of relaxation must somehow work on a much shorter time scale. And correspondingly, what we are looking for are not rigorous invariants of the resistive relaxation, but just invariants or quantities which remain approximately constant on a time scale, on a dynamic time scale, rather than this very, very long resistive time scale.
I didn't quite understand when you said that for ideal relaxation there is an infinite number of invariants.
That is what people say. They mean that you can have, for instance, here you can choose whatever surface you like, and you can integrate the magnetic field over the surface. And if you follow this surface or this in time, then this integral remains constant.
But any magnetic surface?
No, any surface.
Any surface?
Yes.
Or the flux? This
Yeah,
flux
flux.
constraint. Yes,
Yeah.
yes. Any open surface?
And not the same for helicity. Helicity has to be the total.
For the
For
helicity,
the invariant.
you can also you can take in principle any volume. It's a volume integral. However, in order for this expression to be gauge invariant, this surface has to satisfy certain conditions, namely that the magnetic field is tangent on the surface. One can generalize this and consider something which is called relative helicity, and then things become slightly more complicated. Okay, so we are looking for quantities which remain approximately constant on a dynamic time scale. And there the invariance of the ideal relaxation could be a good guide or good indication. And indeed the magnetic helicity turns out to be a very good invariant in this respect. So if we integrate this helicity density, vector potential times magnetic field over a three-dimensional volume, then this expression is invariant if we have the magnetic field to be tangent to the boundary. Okay, this quantity measures the pairwise linkage of magnetic flux in the domain. Now, in our situation, all the magnetic field lines go from the lower boundary to the upper boundary, so this kind of situation can't really arise, but the linkage is equivalent to twist, and in our case we can think of our cylinder as a torus cut open along one plane, and you can see that we can get magnetic helicity from a twist of field lines in this domain. You may argue that in our domain this is actually not satisfied, but if we imply periodic boundary conditions, we can always think of our cylinder with the periodic boundaries identified as a torus, and then it's obvious that this condition is satisfied. Okay, and this this integral turns out to be a pretty good invariant, a robust invariant. And this is the kind of typical scenario which you see if you take one of these braided fields and let them undergo a resistive relaxation, which is in general a very complicated or complex dynamics. You can develop turbulence and so on and so forth. And what you see is that the magnetic energy decreases rather quickly, provided you have a sufficiently high magnetic Reynolds number and also a sufficiently braided magnetic field. And you typically use only a few dynamic time units to do this.
How are you measuring? What does sufficiently braided mean?
Yeah, let me come to this in a second. So the time scale here is something like the alphane crossing time in your domain. So how long does information need from one end of the domain to travel to the other end of the domain? And in a magnetic system, that would be an alphane wave, for instance, which travels from the lower boundary to the upper boundary. And you need just a few of these crossing times for the system to relax. And during this time, the magnetic helicity changes only very, very little. And this has been termed selective decay in the sense that now you could go and try to minimize your magnetic energy under the constraint of keeping the magnetic helicity constant. Okay. Yeah.
You must assume something about the efficiency of dissipation. It must be faster than magnetic resistive time scale.
Yeah, I don't really assume this. This is the result of 3D MHD simulations. But yes,
with which magnetic Prandtl number? That's the question.
The magnetic Prandtl number
Yeah.
is about 1 here, I think.
Really?
So here is, on the other hand, a situation where this kind of scenario I see if I have either a lower magnetic Reynolds number or a field which is only weakly braided. And what I see then is that the relaxation doesn't really work, in the sense that I lose on this dynamic time scale only a little bit of energy, and then this slope is steeper than in this case, and I end up here with much higher values of the energy compared to the initial state. And the difference between the decay of magnetic helicity and magnetic energy is not very substantial. Now, coming to Phil Boylan's question about what is sufficiently braided or weakly braided, the term is not well defined in this context, because we don't know exactly, but that is what we saw. So when we, for instance, increased, okay, let me sketch this here. If I have a system which has field lines in it, at least 3 field lines in it, which do this, kind of sigma 1, sigma 2 to the minus 1 in your notation. Okay, of course, the whole domain is filled with field lines, but there's a structure in this which does this. Then I see something like this. Possibly there's even flatter. Possibly nothing much is going on. If I squeeze two of these into my domain, okay, so second iteration, then I see a little bit of relaxation going on, and if I take three of them, I see this. Okay. So why or where does this come from? Now, there's no hard mathematics for the moment with which I could explain this, but I can wave my hands a little bit. And so the scenario which I think is behind this is, first of all, with higher magnetic Reynolds number, I develop smaller length scales in the turbulent system. But first of all, I have to trigger turbulence. And if you have a very complicated braid, maybe wipe this out. So this is again our domain, and let's say I have a very complicated structure here. Of field lines. Okay. Then the process by which this is simplified is the process of magnetic reconnection. That is, locally, I can turn something like this into something like that. Okay. But it's a local process. Oops. Now, in order to simplify such a complex structure, you need this to happen in quite a high number of cases. Okay. You want to simplify this.
That's changing velocity, is that right?
Actually not. The reason is that I haven't drawn this in all detail. One should rather think of this as two small flux tubes. Okay. And this one here are also two new flux tubes, and they carry some twist. This is a bit hard to see, but the kind of linkage which was present in the initial configuration in the reconnection process turns into twist of these tubes.
So the topology has changed. But
The topology has changed,
not.
but
It's
yeah.
If there were one flux climb,
sorry.
If there were just a single, I think we had this discussion. If you had a singularity, if this were just a single line, then you would have no twist in this line. You would actually,
Yes,
yeah.
yes.
So that is a question of helicity conservation
It's different in a quantized
in a
system.
quantized vortex structure, for instance. Okay, so you need quite a number of these reconnection processes in order to simplify this. Now, each of these reconnection processes has also the capability to trigger others, because it's locally, this reconnection process, when it goes on, it has jets forming, plasma jets forming in coming out of the system in this direction. When these start to straighten out, they they drive out the plasma, and this usually triggers reconnection in another location. So you get these kind of, if you, under certain conditions, you get these cascades of reconnection processes which help the relaxation. So the question whether you get this or that comes down to whether you have initially enough reconnection processes which trigger such a cascade. Okay. And
a simple question.
Yeah.
Are these pictures, is energy normalized to...
yes, so I have no scale here. This is just a qualitative
The
picture.
initial energy in the braid is the same in both cases.
Yes, yes. The actual
If you braid more, you have more initial energy.
you have more initial
Start the
energy.
relaxation, sorry.
Yes, that is true. But you can also braid in a kind of inefficient way. Okay, if I just
Yes.
twist things, I can put as much energy in it as I could get in a more complex braid. So it has to do actually with the braiding, not just with the energy.
Because if you compressed the vertical axis in the top picture, it would look more like the bottom picture.
No,
That's my point.
no. If you would, no, the behavior, the long-time behavior is still different, and you can scale things to match. So,
An even simpler question is the
Yeah.
degree of braidiness matters only per volume of the cylinder, correct?
yes,
Okay.
yes. And maybe at this point I can show you this movie again. So this is what you see here is the current density taken in a cross section across the center of this tube. Okay, current density, actually the modulus of the current density. And initially this is quite a kind of smooth structure, and if you now let this relaxation run, it's a bit too bright here. You see that quite quickly these intense current sheets form and they trigger other current sheets, and the whole thing becomes kind of turbulent motion. The strength of these current sheets goes down in time, so we had to rescale the color scale here for every picture so that we can see something. And the time scale here is not really the dynamic time scale. The dynamic time scale is this one divided by 50. So what we see here is about 6 dynamic time scales. So it's a rather fast process of this relaxation, surprisingly efficient.
Where is the domain? The boundary of what's the computational domain?
The computational domain goes actually further out.
Yeah.
It is goes out to 6. So the whole domain is actually 6, -6 to 6 in both directions.
So I wonder what's the current sheet on the outline.
Oh yes, that's interesting. Yeah, you see this here.
Yeah.
So that comes from the way we set up the braid. You have this braided structure, and towards the boundary you have a potential field, straight field lines. Now this structure in the middle has a little bit more magnetic energy, so there's a bit more magnetic pressure, and during the relaxation this tries to expand a bit and kind of presses into the external field, which eventually keeps it in place. And that is what these current sheets here, which you see. Yes, and this kind of relaxation is also what people, what has been suggested by Taylor for his famous hypothesis of how the reversed field pinch relaxes. So what people have observed is that when they set up this magnetic field in this toroidal vessel, and they switch all the currents on, then first this magnetic field undergoes a turbulent relaxation and then it settles in a certain state. And this state seemed to be more or less independent on the details of this relaxation. And then Taylor came along in 1974 and suggested that this relaxed state is a linear force-free field, and that you can get this force-free field parameter from the total helicity of the initial configuration, assuming that the helicity remains constant in this process. And this was initially quite successful, and then people tried this with different configurations and also applied it to astrophysical plasmas, and the results were in general mixed. Sometimes it worked and sometimes it didn't. So the question is, why does it not work always? And this could be due to the existence of further constraints in our system. So maybe we have additional constraints to this helicity, and that then would maybe force the system out of this lambda equal constant state to a state where lambda is actually a function of the spatial variables.
In Taylor's case, lambda is just a Lagrange multiplier. Right?
Sorry?
Lambda is a Lagrange multiplier here.
You could think of that, yes, as a Lagrange multiplier in the variational principle which you use to derive this. That shows up as a Lagrange multiplier. Yeah.
So what would give it that X dependence? The fact that there's other invariants? Or?
Yes, exactly.
Yeah, yeah.
If you have a whole family of helicity invariants for each magnetic surface,
for instance,
then
yeah.
you need a lambda of X.
Yeah.
So this would be perhaps for a simple configuration where lambda would be constant.
Well, this is assuming that the only serious invariant is the total helicity, which has always been a bit of a hypothesis. I mean,
it's a hypothesis. One should stress this that it's not a rigorous kind of derivation.
He was just very lucky; he got away with it.
Yeah, I mean, there is some kind of physical intuition behind it. It's not just kind of thin air. There's motivation behind it. So then, if there are other invariants, then we need to kind of, most likely they are of topological nature. And so the question is, can we find other topological invariants of our magnetic field? And because there are many topological invariants, like for instance how a field line connects from the lower to the upper boundary would be an ideal topological invariant, but this can be easily broken by resistive dynamics. So we're looking for kind of robust invariants, and these are usually ones which are integrals, which can kind of quantify topological properties. So let's go back and just look at a much simpler case, a two-dimensional field, just to get a kind of feeling for what is going on. Now, a two-dimensional field is easily characterized by a flux function. Okay. And here's a contour plot of such a flux function for some kind of complicated field. The field lines are actually the contours of the flux function, and we characterized here the extrema of this flux function and the saddle points by red and blue dots and black crosses. Okay. And the complete kind of information about this flux function up to deformations, so the topological content, is encoded in the value of the flux function at these points, finite set of points. So here's a simpler example. Again, a contour plot of a flux function. We have 1, 2, 3 extrema, one saddle point, and there's another saddle point somewhere here. And under an ideal dynamics, you could shift around all these contours here. You have a dynamic, an equation like this here, where v is the plasma velocity. But the values at these maxima and saddle points remain the same. And if you want, you can encode these values in a so-called drape graph. So this is a kind of 3D plot of the same information, and you have just one scale A here, and this corresponds to that maximum, and this green dot corresponds to this lower maximum, and this is the minimum. And here I have an x point, which is kind of this x point here, and then I have another x point here, which then connects to the boundary. Okay, so each point on this line corresponds to a contour line in this plot. So now what happens if I let this thing relax? Now the reconnection in 2D is very simple and occurs on x points. Okay, so what happens here is this x point changes its value until it comes closer to this maximum, and then they annihilate each other. So this is kind of simplification of the structure. Okay. And in this simplification, you can find an index which is conserved, the number of O points minus the number of x points. And it's an invariant under reconnection. Now,
this is a maximum annihilating against itself.
Yes.
So it's not a maximum against the minimum.
No. Now, can we find something similar for a flux function of a magnetic braid? Now, in general, this is kind of difficult. The flux function in 2D was constant along field lines. But we know that in magnetic fields generically have ergodic regions of ergodic field lines. So there's little hope to find an integral of motion or a flux function for this kind of thing. Okay, so now we need a little bit to become a bit more precise. This is our setup. Again, we have a cylinder, we have a magnetic field with field lines in the cylinder, and BC is the lower boundary of this cylinder, TC is the top boundary, and our magnetic field is tangent to the side boundary and is periodic on the top and the lower boundary. We also have this condition here, which is we only use here for this example, that the normal magnetic field is actually constant, but this can be relaxed. It's not a stringent condition. Then we define a field line mapping. Okay, so the field lines are defined by this equation. We normalize this here to the z component of the magnetic field, so that the field line parameter S is the same for each level of Z. So for S, let's say, equal 1, all points are at the top boundary. For S, 1/2 in the middle, and so on. And then we can define the time 1 map, so the map which maps all the points from the lower boundary to the upper boundary.
Is there a reason the magnetic field doesn't do this inside or have singularities inside? I mean, why does every field line start at the bottom and go all the way to the top?
That is what we fundamentally assume. There's no, in reality, there will be situations where the magnetic field, for instance, becomes 0 in the domain.
Or could even, you'd have homotopically trivial.
Or could have a closed loop here. But for these magnetic loops on the sun, this is quite a good assumption, because there is a dominant magnetic field component along the loop. Okay, so if we talk now about topologically equivalent flows, then we mean that there is some kind of ambient isotopy which maps these one field to another. So these two fields would be called topologically equivalent if there's an ambient isotopy which maps Fa to Fb, keeping the points fixed. And in terms of MHD, this would correspond, for instance, to an ideal evolution inside this domain, which does not affect the boundary point. Then you get, from the flow of the velocity field, such an ambient isotopy. And there's a neat analogy to what Jean-Luc has showed us, or Phil in his braiding of or stirring of a 2D fluid. If you replace our coordinate S along the cylinder by the time, then you can think of these field lines as the trajectories of a fluid particle. And then you have the periodic orbits, so the field lines which end up at the same point at the top as at the bottom. They can form, they could be thought of as stirring rods, and you can define a braid for these field lines and calculate things like the topological entropy of this braid. But coming back to our magnetic field, we now define a function A as a function of the foot points on the lower boundary as the integral over the vector potential along the field line. If we express it in terms of our field, of our parameter S, and it would be this function A along the field line of B over Bz dx. Now, first problem is that this is not a gauge invariant expression. So if I do a gauge transformation, if I add a gradient to my vector potential, then I can give this function arbitrary values on arbitrary points. In particular, I could make it 0 even for a braided field. Okay, so I have to restrict my gauge conditions in some sensible way, and I do this by imposing the first condition that along a field line on the boundary, here, a vertical line on the boundary, doesn't need to be a field line. The integral of A along this line should be 0. Now, where does that come from? This you can understand if you, with our periodic boundary conditions, we can always turn the cylinder into a torus. Then a line on the boundary would enclose the whole of the torus. The gauge condition here ensures that there is no magnetic flux threading this whole of the torus. So this gauge condition you can interpret in a way that I exclude influence of magnetic fields outside my domain onto my flux function. The second condition here, I require the vector potential on the colloidal part of the vector potential on the lower and upper boundary to be equal to a reference field, and that reference field is a potential field with the same boundary condition. Okay, and this ensures that I give a motivation for this in a second. But with these two conditions, one can show that the topology of the magnetic braid is uniquely defined by this generalized flux function. And we first proved this in a very kind of complicated way, and then later found out there's a much more elegant proof via an analogy with the Hamiltonian system. And so if you write this magnetic field in this domain as a Hamiltonian system, you can do this by using polar coordinates r and phi, and you identify your z coordinate or s coordinate with the time t. And you can write this as a time-dependent Hamiltonian system, where the Hamiltonian is the z component of your vector potential. Your coordinate q is phi, and the corresponding momentum is r a phi. And then this, one can show that this is actually equivalent to the action of this Hamiltonian system.
It looks rather like helicity. I mean, the A dot B in the integral apart from the normalized B.
Yes, you have the right intuition. We'll come to that in a second. And then this is just a quick outline of the proof. You can show that this formulation is equivalent to this equation here, where alpha is the canonical one form. So alpha is P dq. And then you find that this boundary condition, which I showed you, the second boundary condition. Where was it? Here, the boundary condition B. This boundary condition fixes this canonical one form alpha on the boundary. And this helps to prove this theorem that the only case in which two different fields can have the same Hamiltonian action or generalized flux function is when they also have the same time 1 field line mapping. And if they have the same time 1 field line mapping, then the field lines in the domain themselves have to be conjugated. So there has to exist some isotopy G which maps one to the other. Or with other words, they are topologically equivalent. The first gauge condition ensures that the only mappings which leave this one form invariant, the only non-trivial mappings which would leave the one form invariant, namely rigid rotations, are excluded. So this condition is necessary for that. Okay, and then we have a sequence of nice properties of this flux function. So for any two periodic orbits, the difference between these two flux functions on the periodic orbit gives you the flux through the surface between these two periodic orbits. And the function uniquely defines the topology of the braid and is invariant under ideal plasma dynamics. It does, however, change due to reconnection. And now to Keith's question about helicity. This is indeed, this generalized flux function is indeed related to helicity. For this domain, one should use relative helicity to calculate the helicity content in this domain with the reference field BP with a potential field which satisfies the same boundary conditions. It turns out, however, that for our boundary conditions with constant magnetic field on the boundary, this simplifies to integral A of B. So the relative helicity gives you the same value as the standard helicity. And with the gauge condition, you can write this helicity as just an integral over a cross-section on the lower boundary, where you multiply this flux function with the z component of the magnetic field. So you reduce your three-dimensional integral to a two-dimensional integral. And you can then interpret this A, or this generalized flux function, as some kind of helicity per flux. And Mitch Berger came to a similar expression on a quite different way, averaging over winding numbers in a field. He ended up with a similar expression where he can show that this Hamiltonian action is actually the same in this case as his helicity density.
Bz is constant along the field line?
No, it's Bz is, for this example, Bz was constant on the boundary, and the lower boundary and the upper boundary have the same Bz, but in general it varies in the domain. Okay, and so now I show you, I've shown these things before. I show you the result. So this is for our standard example for this braid, which is modeled on this kind of pigtail braid. The corresponding flux function in a cross-section on the lower boundary. Okay, you see that it's a quite a complicated structure. It has very, if you would zoom in, you would see a very, very small length scales here due to the complex field line mapping along this field. And goes from +12 to to minus 12, the value of this function. And in the process of relaxation now, what happens is all these small scale structures disappear and you are left with one big blob of positive and one big blob of negative.
Are there reconnections happening here?
Yes, yes, lots of them.
Lots of reconnections.
The same process as I showed you before in this movie where you saw these turbulent currents. And
You have to do full 3D to get the
Yes.
flux function evolution.
yes,
But
Yeah.
the flux, so when kind of physical, if I think of this as a fluid, physical points are vectors, their flux function is preserved at the points?
if it were an ideal,
Well,
yes.
yeah, well,
Yes.
I mean, even in the simulation, if I follow a particular, is there a way to follow, even talk about following a particular point and seeing that it's what
E-
observed?
Yes, so you always start from the lower boundary. You have here a point x naught,
Right, so
and you follow the field line,
the flux
whatever
function
the
just-
field line does.
Just
Yes,
depends on that field line.
yes,
So that field line evolves in a unique fashion, even with reconnection events.
Yes.
It still connects the bottom and the top.
Yes. Yeah.
Thank you.
So this initial field had a total helicity of 0. So the Taylor hypothesis would say the final state should be a state where this function here is 0 everywhere. So these two blobs should have cancelled in some way in order to reach the Taylor state. But they don't. And this is actually a stable situation, even if you wait arbitrarily long and shake the system and so on, it remains in this state. And so what is preserved here in this process is the maxima and minima of your initial flux function of your Hamiltonian action. And you can visualize this if you want by a similar graph where I now plotted here again the values of all the periodic orbits in this initial configuration, the A values of all these periodic orbits. And then you can see that in the process of relaxation here, the number of these periodic orbits simplifies until you're left with only 2 of them, and their values are pretty close to the initial maxima and minima of your system. There's a bit of dissipation, of overall dissipation. But that is the kind of message. The way in which this graph simplifies means that you can't reach the Taylor state. You have to have a different state which has a maxima and a minimum.
What do the field lines actually look like in that relaxed state?
That's it.
'Cause these are not.
We plotted here field lines along a line, the kind of x-axis on the lower boundary. You can see that
Oh, these
they
are field
twist-
lines, are
they
they?
twist.
I mean, they are field lines.
they are field lines, yeah.
What's
They
the
twist
colour?
right hand.
The color indicates positive and negative A.
A, exactly. Yes.
So there's a sort of right-handed twist in one.
In
or
one side
left-handed,
and left-handed
yeah.
twist. Becomes kind of almost a 2D.
Yeah, be nice if that right-handed and left-handed were more apparent. The trouble is being a
Yeah, it's kind of
projection.
hard. It's very hard to visualize.
To get that, yeah.
Okay, but
So the message is that linkage between linkage goes away fast, while internal twist goes away slow.
yeah, one has to be careful because linkage and twist are very similar things. But I think
Well,
there's,
By twist, he means,
Similar but
I think
different.
of tangent vectors being pushed up
yeah,
by the field lines.
Yeah.
from the bottom to the top into this artificial flow. Is this flux function measuring some amount of rotation of the field?
It does measure.
as you're
It does
pushing
measure rotation in a sense, and that is made precise by this formula for the helicity. So the overall helicity measures twist, overall averaged twist, pairwise linkage, if you want, or twist in this domain. And you can express this in terms of this. We can think of this A as a density of this integral. So it measures some kind of local twist.
This is a
This pigtail, I mean, when you turn it round into a torus, what is are they torus knots?
Yes, so you get the Borromean rings.
This is Borromean rings.
So if you go
right.
outside and look at the
Right.
sculptures in front
Yeah.
of the institute, that's
Right.
what you get.
Uh-huh.
It is possible to write, as I have done many years ago, invariant directly in terms for Borromean and for many others.
Yes,
High order.
if it were just a kind of selection of disjoint flux tubes, you could use these formulas for calculating some kind of third order helicity invariant, yes. But here we have a continuous field, so there are usually no flux surfaces along which you could cut your domain into subdomains. Yeah.
Is the helicity per unit flux a conserved quantity or it changes with time?
It does decay slowly.
Decays.
But
But only due to
only
conductivity?
so you get a decay of the overall helicity
Due to conductivity.
due to the resistivity in the domain.
Okay,
Yeah.
resistivity.
Yeah.
But if it was ideal,
If it were ideal, it would be strictly constant.
in a local sense also. Helicity
Yes,
per-
both
per unit
local
flux.
and global. Yes. So here also you see that the value of these maxima here is about 10, and initially was about 12. Now this is for Reynolds number of 10 to the 3 or so. If you take less, the effect is stronger, and if you take a higher Reynolds number, the effect becomes weaker. So this maxima becomes closer to the maxima of the initial configuration if you take a higher Reynolds number.
You mentioned a few times analogies between open cylinder and torus.
Yeah.
Shouldn't you worry about redistribution of fields? And for instance, you have that integral, line integral, and you said
Yeah.
just to prevent the flux through the opening in torus.
Yes. Yeah.
But it doesn't mean that you should redistribute the fields how they depend on the cross section when you deform one geometry into topology into another.
Yeah. I'm not quite sure whether I understand your question, but I think
Uniform distribution in the cylinder shouldn't be uniform
Yeah.
distribution in torus. That's what I'm saying.
yes. So in the torus, you have a little bit more freedom than in the situation of a braid, because I fixed one cross section of the torus. So I said the velocity on this cross section is 0, so to speak.
But I'm talking about distribution of velocity field
Yeah, the
in all
field
points in the
the
cross
Riemannian
section.
is stronger
So
on the outside.
in a
It should be
torus,
different
you
on
could-
different regions.
the field could actually also redistribute on this cross.
Not only could, they should, in order
Or-
to mimic the uniform cylinder flow. Because
I think partly what he's saying is if you have a torus, the Riemannian metric is different. So the Laplacian is different. Everything is different on a genuine torus as opposed to a flat cylinder with the top and bottom identified. I mean, when you actually change the coordinates, you have to put a curvature.
Oh, you mean because of the curvature?
Yeah, because of the curvature, so the actual
Yeah,
equations
yeah.
in the torus
Yes,
are very
that
different
is of
than on a
course true.
cylinder.
But it's not only
If you would calculate actual force-free field, for instance, in a torus, you would get something different than the force-free
right.
field.
But what I
in
was
a
saying, you
cylinder.
can see these things not even from geometrical point of view, but from topological, because you close the thing and you have to put extra condition that there is no flux through the opening, while for the cylinder there was no external fields, right? So geometry has to do point by point to compensate for that change in the
Well, I don't know, even for the cylinder, you can have a flux, a field around the cylinder, which becomes flux through the hole when you turn it into a torus.
Okay.
So if we think about torus, it's a torus which has one particular cross-section frozen.
Yes,
Okay. That is a
it's a
big
constraint.
change to the
But,
dynamics.
Yeah, we are working on removing this, so allowing the field also to move in this particular cross section. But things become then harder to explain.
I think we're running out of
Yeah.
time, Gunnar.
Fine. I'm done.
You've done very well. Thank you very much. Super.